Year Group 20. Myself, Sai Sandeep, and my teammate Sahil are here to present about Taming an autonomous service vehicle for path following and collision avoidance using deep reinforcement learning. So, the table of contents are introduction, methodology, results and discussion, conclusion. So, coming to the introduction, so basically, the study employs the cutting-edge PPO algorithm to control an autonomous service vehicle, enabling it to navigate a predefined path while avoiding obstacles. So these rangefinder sensors are used to detect obstacles, providing crucial information for the AI agent's decision-making process. So these ASVs have the potential to revolutionize transportation by improving efficiency and reducing emissions. However, ensuring their safety and reliability, effective path planning, which involves path following and collision avoidance. So these path planning methods can be categorized into reactive approaches and deliberate approaches. So these deliberate approaches excel in reaching the destination and avoiding local obstacles, but struggle with dynamic environments and incomplete mapping data. So by dynamically adjusting this behavior, the collision avoidance for ASVs by dynamically adjusting their behavior strikes and balance between staying on the desired route and avoiding obstacles, enhancing the autonomy and decision-making capabilities of ASVs. So by employing the deep reinforcement learning, the study trains an AI agent to effectively navigate ASVs. So the agent adapts its guidance strategy by learning from experience and feedback received from the environment. So with the ability to dynamically adjust between path adherence and collision avoidance, these ASVs can operate more safely and efficiently. So these deep reinforcement learning brings us closer to realizing the full potential of ASVs in transforming transportation systems. So coming to reinforcement learning in this field, a subfield of machine learning holds a promise for controlling an autonomous service vehicles by training AI agents through trial and error in an unknown environment. So this study explores the application of RL in guiding and controlling ASVs for path following and collision avoidance. So this focusing on obstacle avoidance in areas with non-moving circular obstacles for similarity. These RL methods being model-free, learn from experience without relying on detailed vessel dynamics, making them a cost-effective approach to implement guidance systems for ASVs without extensive knowledge of vessel dynamics. So the adaptation of RL in these control systems makes a significant advancement in the robotics and autonomous systems. So by training AI agents through trial and error, and RL surpasses previous AI approaches and offers the potential for intelligent control of ASVs. So this research highlights the importance of reinforcement learning as a cost-effective solution for implementing guidance systems in ASVs. So this reinforcement learning opens up a new possibilities for enhancing the autonomy and efficiency of ASVs in real world applications. So next we'll be continuing by Sun.
Okay, so now getting into the methodology part, like what is the basic idea behind this? So there is an algorithm which is used here that is known as a PPO algorithm, proximal policy optimization, which achieves a desirable balance between implementing simplicity and efficient data utilization, making it highly effective in various continuous environments without the need for extensive hyperparameter tuning. So, this policy gradient methods often suffer from sensitivity to hyperparameter selection, posing a common challenge. So, this considering the significant computational resources required for training and testing agents in a collision avoidance environment, this issue can become a hindering bottleneck in our research. Uh, like as we know, we'll be having the environment agent and rewards. So in the environment, what all the elements will be present in the environment to justify to ensure that the agent can effectively operate in an ocean environment with obstacles while adhering to a predefined path and avoiding collisions. It is essential to create a diverse set of training environments. So these environments need to encompass a broad spectrum of challenges and enabling the trained agent generalize its acquired behaviors to unfamiliar obstacles landscapes resembling real world vessel deployment. So this generate path with obstacles is an another algorithm which is used here that provides a solution for generating new and independent training environments. This aims to strike a balance between the proximity of obstacles to the path and the density of obstacles with the environment. So both the path and with the environment. And if the obstacle density is too low, then the agent may struggle to perform well in environments with a higher density of obstacles. To address these concerns, uh, they proposed an algorithm which generates random training environments that reflect varying obstacle placements. By following this procedure, the researchers aim to ensure that the trained agent develop robust and adaptive behaviors. Now coming to the agent, like what all the factors that will be including in the agent. While the reinforcement learning agent may be initially perceived as the vessel in the context of reinforcement learning in the total whole, so a more accurate perspective is to consider it as the guidance mechanism that directs and controls the vessel. The agent's primary function is to generate control signals which manipulate the vessel's actuators, guiding its actions. So the accurate definition of the state, defined as S, holds significant importance in shaping the decision-making process of the agent. So the information provided to the agent should possess enough fidelity to facilitate logical guidance decisions. To achieve this balance, it is natural to include separate observation features that represent the vessel's path following performance and the proximity of obstacles. So this approach allows the agent to have a good observation of the environment without introducing unnecessary complexity and potential performance issues. Coming to the path following, like how the agent follows the path without any collision, with any collision with obstacles. The agent needs to know how the vessel's current position and orientation aligns with the desired path, and also concept often used for guidance purposes are useful in order to formalize this. So here they considered a one-dimensional manifold equation desired path. Uh, and a common and intuitive method for updating the path variable is to iteratively compute the value that results in the minimum distance between the vessel and the path using Newton's method. So we have an advantage by using this Newton's method is that it only guarantees a local optimum, which proves beneficial in the context of preventing sudden jumps in the path variable. Coming to the obstacle detection. So, in order to avoid the obstacle, we should first detect it, right? So, in order to do that, incorporating rangefinder sensors for obstacle avoidance represents a sensible decision as it corresponds to the reactive navigation system commonly utilized in real-world vessels. So, these vessels often rely on the rangefinder or camera-based solutions. This practical approach enables a relatively smooth transition from simulated environments to real-world applications, which are widely accessible rangefinder sensors such as LiDAR, radar, and sonar. These are sensors. So here in this project, they used 225 sensors, providing a visual span of 4 pi by 3 radians. So these are the reduced number of sensors reduced number of sensors could potentially achieve similar performance. So 225 sensors were selected to prevent potential drawbacks arising from a limited sensor setup. So these cautions decision to apply a 240-degree field of vision was driven by the aim to ensure network size feasibility and optimize the convergence of the employee training algorithm. Coming to the rewards which I have to give to the like agent. So the agent should ideally receive its award reward after either getting to the desired location or colliding. However, since there are a few of the reward functions, so the agent finds learning to be incredibly challenging. This emphasizes the required for a consistent indication of incentive to motivate the agent towards better performance. So here they had developed a reward function R of t that was suitable for the given complexity of the objective task, and the RL agents to misuse the reward function in every way imaginably. So in order for path following performances, it is reasonable to reward the agent for minimizing the absolute cross-track error in order to encourage the planned course. Using a Gaussian reward function, which is a kind of a function with a reward function with a sufficient standard deviation for this objective, they hypothesized that the exponential term has considerably has more suitable features for this purpose due to its longer tails, rewarding the agent for a modest improvement to an undesirable location. So the agent will not receive a reward regardless of the cross-track error if it remains immobile or if the course error reaches 90, which is a set, which the number is set, like the bars are set 90, which is undesirable. Coming to the obstacle avoidance performance, it seems that it is very sensible to punish the agent for the presence of nearby barriers in a strictly escalating manner in order to encourage obstacle avoiding conduct. So by noting that the severity of the obstacle closeness, very closely, does not increase linearly with distance, but instead increases in some more or less exponential manners in terms of exponential, and that the severity of obstacle closeness depends on the orientation of the vessel. So and in the coming to the total reward, obstacle avoidance and the environment agent to discourage the agent from just staying motionless in a secure location, which would provide a reward of zero given the preceding reward function. They added a constant living penalty, which re-exists to the overall reward function. And choosing the best value is also a must feature. So choosing the best value for the trade-off parameter is a very difficult task. So this relates to the core difficulty addressed in this study, and namely how to avoid these barriers while remaining on the target path in order to avoid the collisions. And as a result, they sampled at a random from a probability distribution and initialize it at each reset of the environment. The entire observation vector in the RL terms to represent it as a state S consists of the features that describe the vessel's position and orientation with respect to the path. And in the training process, uh, the okay, so here Sai Sandeep will be continuing.
So coming to the results and discussions. So during the training process, the agent underwent 3,903 episodes, equivalent to approximately 5 million simulated time steps of 0.1 seconds each. So training reached a steady state while with all monitored metrics stabilizing using an Intel Core i7 CPU utilizing an 8 parallel simulation scenarios to expedite convergence. So the entire process took approximately 48 hours. So this test phase, each value has tested in 100 episodes during randomly generated route following environments based on algorithms provided in the methodology. So the testing was conducted without restrictions on the sensor suite. So coming to the next simulation part, simulations were conducted for each agent in 4 quartile test cases. So this table emerges or highlights the distinct behaviors of the agents among the elevated reinforcement learning algorithms. The proximal policy optimization algorithm agent demonstrated superior performance, while an asynchronous advantage Arctic critic agent exhibited the lowest competence. So these findings suggest that a React to RL agent trained using PPO algorithm excels in successful navigating the combined challenges of path following and collision avoidance. So the agent's inclination towards prioritizing path adherence over collision avoidance influences its performance, creating a trade-off between collision rate and path following capacity. So notably, the collision avoidance rate reaches a stable value of 100% when employing the sufficiently smaller parameter values. So these results highlight the effectiveness of PPO-based reactive RL agent in addressing the path following and collision avoidance requirements, showcasing its potential for enhancing the autonomous navigation capabilities for surface vehicles. So coming to the graph-based experimental analysis, so it may be formalized that the patterns can be described by straightforward parametric functions of by plotting the test requirements against. So we use the Levenberg-Marquardt curve fit method offered by the Python module SciPy to construct a non-linear least square estimation for model parameters after choosing the suitable parameterizations. So these figures show the fitted models for our evaluation measures. So coming to the conclusion part, reinforcement learning, especially the proximal policy optimization algorithm, has been demonstrated successfully for controlling of vessels in navigating the predefined paths and avoiding obstacles without relying on maps. So these agents observation vectors and reward function design, including techniques like feasibility pooling and incorporating the reward trade-off parameters like lambda, enable adaptive guidance strategies between path adherence and collision avoidance. So existing testing algorithms has shown promising results that with the agent achieving an high success rate of over 90% for strict path adherence and close to 100% for a defensive strategy. So even in challenging environments with dense obstacles, for this further research, it could explore learning the reward trade-off parameters like lambda from automatic identification system data to further enhance the agent's performance. So here we conclude the topic of vehicular networks by group 20. Thank you.